good to be here, actually. I worked here around about 2001. Was the first time we deployed our multi-beam sonar to the area, and that was the start of a multi-year program of surveying in the park and beyond the park towards Manitoulin. Just a few points, I guess, before I get going with this. I'm not a scientist. I'm a commissioned Canada Land Surveyor, and Canada Land Surveyors are, well, they can be licensed to work in national parks, so I feel somewhat at home with park all around and a water park to the north of us. That's where my area of expertise comes in. Also, with all the divers here, I think I need to appeal to you. I got certified about 30 years ago and actually bought my first kit at Supreme Divers, and I still have my Con Shelf 4 regulator, and I remember going to dive on some moorings in the Saugeen, and I can't remember the name of the dive shop. It was in Port Elgin, and the fellow there took a look at my gear. He said, "What are you trying to do, kill yourself?" But I still have it. The rig's great, and unfortunately, I've never dove here. I've dove just about everywhere else I could, but I think I'm saving this area up as on the bucket list for retirement, so I'm looking forward to that. As a segue to Dr. Harper's presentation, I believe that hydrographers do it deeper too. We do it by remote sensing, and I didn't think that was going to be funny, but yeah, with remote sensing, I think most people think satellites up in space and they're looking down on the Earth, but we use sonar and we use laser, and that's what this talk is going to get into. I don't know if I've got 45 minutes here. I don't want to kill you with PowerPoint. I guess also another caveat here is I'm going to throw some acronyms at you. It's good to see that some of the acronyms I have already been talked about. I see we've got the Navy here. That I know they eat acronyms for breakfast. We use them, and it helps. So if you're puzzled, just say, hey, what is that three-letter word that you're talking about? LiDAR, being one of the sensors I'm going to talk about, is essentially an acronym. It's light and detection and ranging, and it's in this case, it's bathymetric LiDAR that we're going to predominantly be covering. So I'm also going to be going back and forth from notes, and if anyone's spoken in public before, I think there's two ways of doing it. You're going to read your notes, or you're going to just wing it. So I'm going to try and wing it and read notes. If I have a moment, just bear with me. I'll be coming back to reality again. But also, like to, I guess, get going on this to recognize the merits of side scan. And although we're talking about bathymetric systems here, multi-beam sonar, LiDAR, side scan has been a tool that we've used. We've worked extensively with our friends in Parks Canada, UAS, and in recent years, that work has been actually in the Arctic looking for the Franklin expedition. The configuration that you see in the upper left is the traditional application of sonar for mapping and hydrographic data acquisition, where we would be using a single beam, that's that pencil point beam you see coming down there, in conjunction with a side scan sonar. The side scan sonar essentially tells us what's going on beyond the range of that small single beam. The single beam is giving us quantitative information. It's actually giving us depth, where it's important that I get it clear that with side scan, you're getting a wonderful high resolution image. It's a two-dimensional image of the seabed. But in the early days of pioneering digital post-processing techniques, one of the things we would do would take all the information that we've collected with the single beam, create a digital terrain model, and then take the digitally reprocessed side scan image and drape that over top So essentially starting to create the kind of interesting imagery that we're now able to do in one package with multi-beam, and to a lesser degree with the resolutions that we have with LiDAR. On the right is what I consider to be probably the creme de la creme in terms of side scan imagery. 900 kilohertz, I guess the key word, the take-home message here is the higher the frequency, the higher the resolution. And this is from I believe a UUV 3500 sensor produced by L3 Klein. And just a wonderful image. You can see rock outcrops, sand waves, and that sensor is resolving targets down to centimeter resolution. I'm having a moment now. Okay. Okay, got that. Good. Okay. This is side scan imagery from a lower resolution system, 300 kilohertz. I recall this was a Klein 3000 system, and sorry, it's not a new rec. It's for these waters, but it was a new rec for us. It was a vessel that we found in Hamilton Harbor, which, if you can deal with all the funk in Hamilton Harbor, you want to go check it out. I think the zebra mussels are likely clearing things up. You might get a good look at it. It's only in about 17 meters of water, and it is marked on the chart now. This is from a surface-mounted system, as opposed to what you saw in the previous image. It wasn't a towed system. We actually have the sonar unit hull-mounted, and we're scanning along. Concurrent to when this was surveyed, we were running a single beam system to get our depth. In the same frequency range, 300 kilohertz, this is a multi-beam sonar image of a wreck, and it is here. This is the Arabia. And you'll notice on some of these slides, and I gather these, my deck, as well as the others, will be available afterwards, there's going to be some reference numbers attached to the images. This information is available to the public, so another take-home message. I think part of the reason I'm here is not only to try and give you a bit of a primer on high-resolution seabed imagery, but also to let you know that this data is available to the public. So for folks who are doing research, I'm a strong proponent of the belief that the work that we do is the base mapping for any subsequent research that works in the environment. So it's like, for example, you're going to do research on a hillside, and you want to locate gopher holes. You're obviously going to want to have a base map. You want to have a topo map showing the lay of the land. Then you can position your gopher holes. In this case, we are holding ourselves out as the organization in the federal government that has a lot of information that can help in other research endeavors. So just so you know, it's there. So what I'd like to then speak to, and I'm going to read, I guess, multi-beam sonar technology has brought about a fusion of high-resolution imagery, which you see here, with depth measurement in one package. So previously we'd have to run single beam and then tow the side scan. It's all here. So each one of these pixels is precisely georeferenced. And these images that you see here can be made available as georeferenced TIFFs. Lakebed imagery produced from multi-beam sonar is truly three-dimensional and georeferenced. As the name suggests, the sonar system produces multiple beams of sound, upwards of 300 beams per ping. And a system like this will ping upwards of 20 times per second. So you can imagine how much data now is just being collected. Discrete data points all being brought together through a processor, which at the end of the day, we're able to create these highly precise georeferenced images of the seabed. So each ping creates a swath profile of the lake bed. And these swaths, and you saw the swath the side scan fish produced, these swaths aren't quite as wide, but they're about 3 times, typically 3 times water depth, or 3 times the height of the projector, the sonar transducer, above the seabed. High-frequency sonar results in shallow water can yield sub-decimeter resolutions, and these are only limited in measurement precision by the positioning technology chosen for surveying. So multi-beam sonar was introduced to CHS in the mid-90s. Although the technology had been developed years earlier, the positioning technology had not yet caught up. Because we know GPS really came commercially available in the early 90s. It was not only trying to get GPS technology to the point where we could resolve centimeter positioning, it was also a matter of being able to precisely orient the attitude and heading of the vessel while this sonar beam was being projected. So in that regard, we also needed to introduce inertial measurement systems. And our launches use military spec secret squirrel inertial systems that precisely orient the vessel at an update rate of about 100 times a second. So we're getting 100 hertz of position and orientation, marrying up with about 20 hertz of sonar. And that technology has finally come of age, and we can now, with confidence, produce this type of data with accuracies, and I'll get into some of the accuracies later on, that are satisfactory for nautical charting, because that's our core mandate. We make navigational charts, and as a scientific function, we support other research with our imagery. So we're taking advantage of all this technology now, and we'll talk about accuracy. Positional accuracy in hydrographic terms is expressed as the total propagated uncertainty. So here comes an acronym, TPU. This is the total propagated uncertainty of all sensors used to obtain a specific measurement. So we've got 2 types of uncertainty, horizontal and vertical. So horizontal, where are we on the face of the Earth? How accurate do we know that location? And then how accurate do we know the location of the depth that we are obtaining off to one side of the vessel with this swath? And then we have vertical uncertainty. How accurate do we know the depth or height of that target above the seabed? Vertical TPU is dependent upon the ranging accuracy of the sensor and of water level measurement. So really, we've got the sensors down pat. The tricky part now is how well do we know what the water levels are doing? And by that, how accurately is our tide or water level gauge? We have a gauge here at Tobermory, and we've got gauges throughout the Great Lakes system. And this is primarily where we get our information about water levels, and we apply those water levels to be able to resolve the true height or depth of features relative to something called chart datum. So if you used nautical charts, you know that on the Great Lakes we have something called International Great Lakes Datum, and that reference datum has essentially a vertical value for each and every lake, and it's to that value that we set the zero of our charts. So when you see depths on a chart, they're relative to that datum value. Advances in GPS positioning have brought us to the point now where we can position ourselves vertically relative to the ellipsoid. Ellipsoid is kind of like this theoretical surface that satellites recognize as the shape of the Earth, for lack of better explanation. And we now have the ability to relate that ellipsoid to chart datum. The long and short of it is we're getting away from using tide gauges and hoping that we can get better resolution around that vertical accuracy. So what are we talking about in accuracies here? Horizontally, with these high precision GPS systems, we're seeing somewhere in around 0.2 to 0.3 meters horizontally and 0.5 meters vertically. The story changes for LiDAR. and we'll get to that. This is the launch that we use primarily to survey throughout the park between 2001 and 2007. This is the Canadian survey launch, Petrel. And at the time, we were using a system called a EM3000. This vessel has now since been pimped out with some more high-end equipment. The EM3000 would get us down to about 180 meters water depth. The EM2040 has a variable frequency on it. We can adjust between 200 and 400 kilohertz, and at the 200 kilohertz level, get down as much as 500 meters in water depth. On the LiDAR side, it's airborne. We've been working with a company called Fugo Pelagos for a number of years. Their sensor, which is Optec's Shoals 1000T. Optec is a Canadian company, so they're actually local to the GTA. That package you see there is about the size of a small refrigerator. It's put in the back of that King Air, and that King Air flies at about 1,200 feet above lake level. And the system you see actually pulses right through the bottom of the aircraft, sending a laser out to detect the lake bed or seabed. So just going back before I get too far ahead of myself here, so as part of a collaborative effort between CHS, the Geological Survey of Canada, and Parks Canada, multi-beam surveys of Fathom 5 were begun in 2001. At the time, the sonar system of choice was the EM3000 shallow water multi-beam. The coverage, and we'll see that shortly, the coverage we obtained between those years amounted to 154 square kilometers. And that was done over 46 operational days, about 276 hours of sounding. You'll see at the end the comparison, the relative data collection rates between LiDAR and multi-beam and the trade-offs. During that time, many known wrecks were mapped. You saw the image there of the Arabia. Notably, what we were able to scan quite well was the evidence of a post-glacial waterfall northeast of Dunk's Point, and I've seen reference to that in the park's literature. The height of this waterfall rivals that of Niagara Falls. This was also our first opportunity to test the maximum depth of the EM3000 because it falls off to well beyond 100 meters east of Dunk's. Okay. So I guess, multi-beam, LiDAR, neither one are the magic bullet for bathymetric mapping. They each have their own applications. I guess the main limitation of any sonar system, and multi-beam is no exception to this, is the inability to sense in extremely shallow water. This is because the system is always going to be limited by the draft of the vessel, particularly where shoal waters present a risk of grounding. Secondly, the geometry of the multi-beam swath is such that the extent of coverage is directly proportionate to water depth. So the shallower you go, the narrower that swath, the tighter the line spacing. And that boat's got to be running lines that are 5 meters apart to get total coverage in water depths under 5 meters. Towards the end of that program, around 2007, here in the park, plans were made but never implemented until very recently to conduct further bathymetric surveys using bathymetric LiDAR. And what we had essentially last fall was an opportunity to extend coverage from surveys of the south coast of Manitoulin down into the park. So I took the plan that was put out in 2007 and incorporated it with our program, and we were able to get some coverage, which you'll be seeing in the upcoming slides. So back to Bathy LiDAR, similar to the challenges we faced with multi-beam, The positioning technology of the day needed to evolve considerably so we could do accurate data capture with LiDAR. LiDAR was nothing new to us. We used LiDAR back in the 80s. A more primitive system called the Larsen 300 was flown up the west side of the Bruce and in various parts of the Western Arctic, but the early systems had some limitations. Obviously, the positioning. We didn't have GPS then. We were using radio positioning systems, and the inertial systems used to measure the aircraft's heading and attitude were very rudimentary. So a lot of positional error involved with that. But I guess more critically, and this was sort of the Achilles heel of the early LiDAR systems, was this business of shallow water detection. And you'll see in the operating principles here, going right to the point, the image you see on the right is essentially what one would see while they're watching the returns coming in from the sensor on the aircraft. It's been likened to The Matrix, if anyone's seen the movie where Buddy's watching the code just scrolling down the screen and he's understanding it, but you're looking at it and it just looks like digital rainfall. Trying to understand LiDAR is somewhat like that. The folks who use this are highly specialized in their ability to interpret the wavelengths. In the world of sonar, we see a nice bottom trace. It's kind of easy. You can see the bottom. LiDAR, they deal in these waveforms, but the principle behind LiDAR is that the laser will bounce first off the surface, you get your first blip, and then off the bottom you get your second blip. And then knowing the speed of light, we are able to essentially take time between the blips and determine the depth. Pretty easy, until you get to the point where you're in such shallow water that you can't even discern one blip from the other. And that's kind of where the technology hit a roadblock back in the 80s. And it has since evolved through post-processing software that operators now are able to break this apart further and discern the time difference between the surface and bottom return, and they call it the shallow water algorithm. And it was a major breakthrough, and it's now brought forward the evolution of LiDAR as we know it now into a system that can survey right up to the waterline and then keep going. And I guess another take-home message I'd like to pass on is with LiDAR, we have that ability. It's one of the great uses of LiDAR is that there is no seam between bathymetric and topographic data acquisition. We have that land-sea interface now mapped, and we can accurately define high water line, low water line, and improve our charts that way. Oh yeah, so just as I guess a note, a factoid, the whole shallow water thing tended to be a problem in depths under 3 meters. Well, depths under 3 meters are a going concern to you if you're a boater. You want to know what's coming up. So again, that was kind of the showstopper for the technology, and we took a break from it for about 2 decades until they were able to figure that one out. And Optech, again, Canadian company who we've worked with, have done just that. Another point of contention, I guess, with LiDAR is, the business of target detection. So we talk about sonar and how side scan can resolve targets down to centimeter size. Multi-beam, depending on the frequency and the individual beam widths, can resolve targets into sub-decimeter size. But what could LiDAR do? And tests were done. This slide is just to demonstrate that in order to meet International Hydrographic Organization standards for Order 1 surveys, I'll show you the chart later, LiDAR has been proven to detect a cube 2 meters square. And that's a good thing. So here's the combined coverage, and just for reference sake, those 2 arrows are are pointing to areas that I'm showing in this presentation. The arrow on the right is the survey area that we covered off back in 2001 to map out the Arabia, and the arrow on the left points to the area where I've done the surface comparisons, essentially to see, in the case of just receiving the deliverables on this recent project, whether or not the contractor was on the mark with the required accuracies for the LiDAR acquisition. So just getting back to TPU and LiDAR, it's not as accurate as sonar, positionally and horizontally and vertically. We're looking at anywhere from 0.3 of a meter to 1 meter accuracies in depths of 30 meters. And sorry, I'll correct that. 0.3 of a meter in 1 meter of water depth and 0.5 of a meter in 30 meters of water depth. So it's a sliding scale. The deeper you go, the greater the inaccuracy of the depth measurement system. And then horizontally, estimates and tests have come up with about 1.5 meters in positional accuracy. What that means is the target on the seabed, not the aircraft, but the target that you're actually trying to sense, can be positioned within 1.5 meters. The work that you see in the sort of rainbow color-coded imagery, that is the LiDAR coverage. And pretty well south of Manitoulin is the area I'm throwing the stats at. We were able to cover the same amount of ground that was covered in 7 years of program using the multi-beam system with only 5 flights. So essentially a period of 1.5 operational days, we had the aircraft running 24/7. So about 18 hours and 5 flights, we were able to cover off the same amount of territory as we did using the multi-beam sonar. And just to reiterate, the multi-beam sonar is the area you see in pink. So again, if any of you are doing research in the park or beyond the park, just to let you know, this kind of information is available. It's publicly available for research use. So what did we get in the surface comparison analysis? Just zooming in on the area around Cove Island. Again, you see the area mapped out for the Arabia site, but to the left, where I did the surface comparison analysis, positionally, everything was lining up. We're talking within a decimeter of each other, but in the vertical, we were seeing accuracies of anywhere from 0.1 to 0.5 of a meter, which jives with the vertical total propagated uncertainty of the LiDAR system. Something else to note, the multi-beam that you see here is sampled at about 2 decimeter resolution. When we go to create the images that we would be keeping in the database, that the images that would be available to the public, we're gridding those at about 1 meter. The resolution of the LiDAR is considerably less. The picture we see here of the LiDAR coverage and that coverage you see of Cove Island is also from LiDAR, is at a 5 meter resolution. Still creates a nice picture. Zooming in further, I've taken that pink area of multi-beam and actually displayed the resulting grid. So you can see the notable differences in resolution. I've applied a transparency to the LiDAR imagery just to show the underlying hydrography. So we've actually got this superimposed on our electronic chart of the area. couple arrows with question points there. What's with the data holidays, you might ask? Well, the thing about LiDAR is because it's laser, it's light, it will only penetrate as far as it can see. So if there's a lot of turbidity in the water, it's only going to go as far as the turbidity. So much like you folks diving and taking photography and noticing that there are times, particularly after storm activity, when things are really dished up, you're not going to see much. The LiDAR isn't going to see much. So when it comes to planning LiDAR missions, one of our biggest concerns isn't just getting everything there and the people in place, but hoping that we get the weather for it. And two of the things that tend to snooker us are cloud cover. Again, the aircraft needs to fly at about 1,200 feet. If we're getting low cloud, no worky. And turbidity. If we're getting a lot of turbidity in the water column, we're not going to get bang for our buck. One day we may see down 8 meters, the next we may see 30. And it changes like that. And as Marc-Andre would recall, that we've had these frustrations in working in the Arctic where we've deployed LiDAR on, in around the Franklin search areas where it will change with the weather. So the data holiday that you see there is basically where the system has gone to extinction. Now that said, that's about 25, 30 meters water depth, which is pretty darn good. In Caribbean waters, LiDAR will go as far as 60, or so they say. So how do we put it all together? Well, as I said, no one technology is the magic bullet. The idea here is that LiDAR will give us the nice inshore coverage right up to and onshore into the topo regions, and the multi-beam will be used for deep water acquisition. Again, we want to keep our launch out of the rock pile. The systems aboard these launches are not cheap, and there's a lot of expensive bling hanging off the bottom of the launch in the way of transducers. So we want to keep them away from the rocks. So our game plan is to let the LiDAR do that and then use the multi-beam to do bathymetric acquisition in the deeper waters. The other question mark that I'm pointing to there is what's all that buff color around the shoreline? The resolution, it's not yet been processed, but what we're actually seeing there are two distinct contours. We're seeing low water line and high water line. So again, because the LiDAR is precisely vertically referenced against IGLD, we can then model the LiDAR and resolve our topo contours. If we wanted to, we could continue to generate contours inshore and into the deep, but a big concern to us is nailing down what is the shoreline, what is the high water line, what is the low water line. And you'll see just by this example, when we initially built this chart, we were erring on the side of caution. And so what is the low water line is actually appearing as coastline. This is where this kind of observation is going to help us improve our charting accuracies. But the important thing is we're catching all the hazards. So in reviewing this data, it's reviewed against existing charts, and we're just checking to see that there are no uncharted features, that we're hitting all the shoals. And this is where visualization systems like that software Flater Mouse you might have seen in the previous slide comes in handy, because then we can just visualize and do our cleaning that way. Again, the difference between LiDAR and multi-beam, LiDAR is the matrix. Multi-beam, there's a lot more tangible visualization that goes on when it comes to cleaning the data, because we're actually seeing the seabed as it's being acquired, which is kind of neat. So those results. Just did this simple table to show the results of relative accuracies, resolution between the two systems, and the resulting coverage. I guess the important numbers are, what are we getting in accuracy? Can we rely on LiDAR as a proven sensor for nautical charting? The answer is yes. Those HTPU and VTPU accuracies that you see there fall within recognized international standards for nautical charting. And but where we find big differences, departures, and it depends on the application of the imagery. We're seeing a difference in our ability to image, essentially create those pretty pictures that you see. Whereas with the shoals, we can create a 5-meter grid. So that means each pixel that you see in that image is 5 meters apart versus a 1-meter gridded image with the multi-beam. And then the bang for the buck side of things, the amount of ground you can cover using one system versus the other, it is considerable. But then again, we can run the multi-beam launch in fog. We can run the multi-beam launch if there's a lot of turbidity. We can still carry on with the program, whereas when it comes to flying, we're very weather dependent, and also in terms of sensing, we're very weather dependent through the water column. And because the timing of this previous job was late in the season, we had another thing going against us, and that was ice. And as you probably are aware of, we had ice come early this year, and much to our surprise, where we've been enjoying relatively ice-free winters, this year it started in on us in November. And when we got going on the project, we were already getting 3 4/10 coverage in some of the back bays. And that created another scenario. So it was a constant back and forth with Canadian Ice Services to monitor what is forming and where can we put the aircraft to avoid ice cover. Coupled with the fact that, I don't know if you remember, back in December, it was blowing a gale for weeks on end out of the west. Just blowing like stink. And what did that do? It just dished up everything. And so now we've got high turbidity levels. So in the areas where we thought we'd get pay dirt, like the back bays where we don't want to send the multi-beam boat, we're getting turbidity. The good news is we had some money left over, and we're going back and we're going to fill in some of those data holidays and cover off all the blanks. I think it's worth to mention, I don't have an image showing this. Another nice spin-off with both these technologies is we get something called backscatter. In the world of LiDAR, it's called reflectance, but it is essentially, it's mapping of the image return, or the intensity of the return. And from that information, we can actually determine what type of seabed there is there without actually putting down a grab to sample. So the intensity returns through post-processed analysis will tell us whether or not we've got sand, mud, clay, rock, and that is very helpful, because when it comes to producing nautical charts, we want to be able to put bottom quality samples on the charts so mariners know where their anchor is going to hold. But from the scientific aspect, there's a lot of folks who are particularly on the habitat management side, that want to know what kind of seabed is there, because they understand the correlation between the bottom type and the type of critters that want to live there. So just a quick overview of the standards again. Because we build navigational charts are international. They got to be understood, whether you're sailing from the UK, or you're sailing from Japan, or you're in Canadian waters. These standards allow us to maintain consistency in the presentation and the reliability of the information that we publish on our nautical charts. So all to say is that these standards have been established internationally. Every country who is a member of the International Hydrographic Organization adheres to these standards. And the one I just wanted to bring your attention to, within the Order 1 column at the very bottom, system detection capability, that's where that 2-meter cube comes in. That's sort of the proof that, yes, LiDAR can be used for bathymetric observations and charting applications. In the world of electronic charts, if anybody's used what's called a vector electronic charts, we've got something called CATSOC, and it's Category Zone of Confidence. So with an electronic or an ENC chart, you can literally click on the screen and get information about the bathymetry in that area. We use something called CATSOC. It's an international standard for determining the type of coverage and indicating to the mariner some extent of confidence and reliability in what they're seeing there, knowing that we have different resolutions and different measurement accuracies. So if you're working on the surface, not so bad if you've got 30 meters of water below you and the measurement accuracy of the system is maybe plus or minus 1 meter. But if you're in a sub and you're running that submarine along the bottom, you may want to know the accuracy of our measurement of the seabed because you're working that much more closer to the bottom. But on the lakes, we've got something called under-keel clearance, particularly in the seaways where a lot of the tonnage is being moved, St. Clair River, Detroit River, St. Lawrence River. A lot of these vessels are going through with minimal water depth underneath their keels. So this is where these high-resolution systems, particularly multi-beam, becomes critical because we need to provide that confidence to the mariner that if the chart says they're going to have, half a meter under their keel, they better darn well have a half a meter under their keel as they're going up the St. Clair. And just wanted to flash this one up here because this is what it was looking like by the time we were getting out of Dodge with the LiDAR survey. This is taken over the passage between Tobermory and Manitoulin, and you can see the ice was filling in. And from day to day, this would change, further frustrating our efforts. One day it would be wide open, the next we'd have 3 or 4 tenths of ice in the area. But it's all part of the fun and the challenge of doing this work. I hope I've been able to convey some of the excitement I feel about what I do. I think like Marc-Andre, I've got a bit of a dream job in that I love to go to work and I love to talk about what I do, and it's been a pleasure speaking with you today. Thank you.